question about ggplot was earlier. This is by far my favorite book on how to do R. It's called R for Data Science by Wickham and Grolemund. And I know I have a link to it in the slide deck, but it's open, it's available online for free, so you don't have to buy it. It's such a good book that I chose to buy it, but they have a couple of chapters on ggplot as an example of, if you wanted to learn more about that really powerful way to visualize data. I really recommend that book for learning and for learning more how to do ggplot, and then also some of these principles with the tidyverse. Really valuable tool to help you do some of that. Okay, well, we're going to pivot a little bit. I know we've got about 40 minutes left, so I have some slides now on statistics and some common statistical approaches that we think about when we do forestry. Let's see. I'm just going to do slideshow. And so here's a graph of what I call the statistics workflow, or the data analysis workflow. We often have a problem, we identify it, we collect some data to help answer that problem. Maybe that's where our sampling comes in. And then we need to process and clean those data, but we should visualize the data. I'm a fan of, one big takeaway that I like to tell people is that as soon as you get the data, have a look at it, visualize it, get to know the data through some exploratory analysis, and then do your statistics, and then visualize the data again. And so I'm always a big fan of visualizing the data at these different processes across your statistics workflow. This shows the very, very large topic of statistics and where things fit. And so within statistics, we can think about using statistics to describe data. And so we might do that with things like ggplot, with graphs and visualizations. Or we also might look at things like the mean and the median and some of the other measures of central tendency. We might look at the distribution of data, how individual data points are relative to other data points. And so we think about those as descriptive statistics. But we use a lot of statistics to do things like hypothesis testing and to do things like estimation through linear regression and some of these other concepts that we're interested in. And so that's really what I'll spend a lot of the time on today, is this estimation piece. And what I mean by that is mostly the linear regression and some of the other concepts related to regression. I outlined just a couple of what I call core statistical concepts for a forester. And so I've listed those here. Analysis of variance is really important, in particular for folks that are kind of very research focused, that use data from experiments. Understanding what analysis of variance is really important. So that allows you to basically take into account in the experimental design framework different treatments and their effects on an outcome. And so it's a really important topic. A correlation is really tied with regression in a lot of ways. But if you think about regression, things like simple linear regression, where you're using just one predictor to predict something of interest, or multiple linear regression, where you have lots of different predictors for something of interest. Those are important concepts. Logistic regression as well, if you wanted to estimate whether or not something happens or not, kind of a binary outcome, say, will this tree die or will this tree survive, over some time period. In forestry, we also have a lot of count data. And so many of the things we think about with count data are like data as integers. And so we have trees, we can't have 1.2 trees, we have 1 tree or 2 trees or 3 trees. And so we think about data in a forestry context as count data oftentimes, and they have a new kind of a different suite of regression tools we could use. And then we do a lot of mixed models where we can incorporate things like randomness or random effects into our modeling efforts. So knowing something about those different regression techniques can help you in your foresters in your toolbox. And then I did add a couple of machine learning techniques. I included random forest and XGBoost there. I won't talk about those a lot, but I do think as you're learning more about artificial intelligence and machine learning being a component of AI, I do think it's important to understand as a forester how some of these tools work. Even if you're not using them yourselves in your own learning, it's important to know how they work and how they operate. So again, in regression context, numerical prediction means predicting something you don't know, where the answer is a number. That's as simple as it is. And so we often have independent variables. This is the information we have. This is things like the diameter of a tree or the species of a tree. And what we want to know are the dependent variables. So these are things like the volume of a tree or the biomass in a tree. And so these dependent variables are often more hard to measure, and that's why we're modeling them, because we have a smaller data set and maybe we want to understand that before we apply it to a larger data set across our forest. I don't have a ton of math, but here's a little bit of math. For many of you, maybe you've seen simple linear regression, or maybe this is the first time. But all we're doing with simple linear regression is we want to know something called y, and we have some parameters associated with that regression, what we call beta 0 and beta 1, the intercept of the regression and the slope of the regression. And we have a variable of interest that we collect. That's our diameter, that's our species that we call x. And then we have some random variability, which we represent by this Greek letter epsilon. And so how do we choose these values? Well, we need to do them in a way that we call the principle of least squares. And so we want to minimize the error. It's kind of like we've tried to do with stratification. We want to, in this case, minimize what we call the residual sums of squares, or if we add up all the errors in our model, we might want to make that as small as possible. That way we have a great line that fits through our data. And so some of the assumptions in regression, I'll just kind of go through these quickly, but I will say that it's important to understand some of the limitations and the assumptions of anything you're doing in regression. In regression, so the means of our population are linear related through time. And so that's why we're doing linear regression. And so that makes sense. Number two, there's a constant variance for every population. And so we represent the variance by, in our case, sigma, or we represent the variance by sigma squared, or the standard deviation, the square root of the variance by sigma. So that's got to be constant throughout your entire population. The response measurements are independent normal random variables that when you hear people say, well, you can't do that statistical technique because the data aren't normally distributed. That's what that means. And so that normal distribution, kind of taking that classic bell-shaped curve that you might see. And there are different ways to test that with the data that you're working with. And then the variables need to be measured without error. And this is actually a common one that's often overlooked. We just assume that when we collect the data have no errors and no warts in them. But there are lots of times where data are measured with error, and that can result in some pretty bad things going bad in a regression context. If you don't have clean data or you don't have normally distributed data, that's not to say you shouldn't use those data. There are lots of ways to transform the data to get them to become normally distributed or to get them to behave in a way that you want to. And so I've listed just a couple of them here in this table. If you have data that are like count data, like 0, 1, 2, 3, you can do something like a square root. The logarithm is a really popular one in forestry. This often turns non-normally distributed data into normally distributed data, doing the logarithmic function. So really commonly used, you'll see that widely used. You can take the reciprocal of something that's often pretty applicable in cases where you have non-zero data. You can do the arcsine. This is a mathematical trigonomic function that you could do with proportions. So there's lots of ways to transform your data to make them behave more well before you do some more statistics on your data. I will mention that forestry data are often nested. And this really makes them well suited to mixed models. And so forestry data are often nested both spatially, and so you can think about, within a context, in the example we just showed, we're measuring forest inventory plots within forest stands, within ownerships. And so from a spatial context, they're nested, but they can also be temporally nested. So again, if we measure the same plot over time, we can temporarily nest a plot inside of one another by taking advantage of that. And our mixed models can also account for those hierarchy within the data. And mixed models take into account fixed effects and random effects. And so as an example, like what we might do is we might say something like, if we want to calculate the volume of a tree, well, we know if we calculate the diameter, that can be a fixed effect because we think that that diameter of the tree is going to relate really well to the volume of the tree. But if we know something like, say, the species of that tree, we might treat the species as a random effect because we might think, well, one species is going to have a different form, it's going to have a different crown, it's going to grow differently than another species. And so we can begin to account for some of that randomness through random effects specified in mixed models. So here's just an example of a forest stand. You might have many of these across the landscape. We have lots of inventory plots measured inside of that forest stand. This is an example of that nested design, plots within stands, within ownerships that we might be looking at. And so linear and mixed effects models have the fixed effects. Like I said, these are what we think about as population average values. This is the diameter of the tree if we're interested in estimating tree volume. And then we have random effects. So for each individual observation, we know that there's some kind of variance or deviation from a fixed parameter. And so you can basically assume some things about the data if you were to employ linear mixed effects. So here's an example. You can make the intercept of a simple linear regression model be random. And so that's what I'm showing here with the little b sub I. Our fixed effects, beta 0 and beta 1, are similar to what they might be in a simple linear regression, but the little b sub I is the random effect for effect I. Say that I might be species in this case. X might be our tree diameter, Y might be our tree volume. We might be interested in specifying a random effect of species on this relationship. And so these different parameters can be random. And so you could pretty much specify where you want your randomness to occur in your model. And so here is an intercept being random. And so you can see the simple linear regression is just a straight line through the data. And so here you can see there are 6 different intercepts for those values. That's because this beta 0 value is going to be changed by little b sub I, which is going to change along the y-axis. And so we can say that the intercept here is random depending on, in our case, maybe this is the species that we're investigating. You could also have the slope be random. And so in this case, they share the same y-intercept, but in this case, the slope changes depending on that. And so you can see the slopes are very different for these different random effects. And so that's an important thing to recognize as we're looking through some of these different implementations of mixed models. And then you can get to the stage, well, you could have a more complex model where not only is your slope random, but your intercept is random too. And so the random intercept term is located here. You can see there are different values along the y-axis, and there are different slopes. And so this is a more complex model that has 2 random effects, little a sub I and little b sub I, you can see there. And then random effects can be nested. And so you can have more than one random effect that are nested upon each other. And so in this case, little sub I represents the ith subject, and I sub j represents the jth subject nested within subject I. And so how that might look is you might have 3 different subjects for I, and then you might have a lot more for subjects J nested within subject I. And so just a lot of complexities you can begin to think about. If you want to try to capture most of the variability given your data, think about random effects and think about applying them to your own forestry situations. Well, as I wrap up this, before we jump into R, I did want to mention a couple of resources. I guess I did mention this book already. This is a great book for, there's not a lot of statistics. You know, it's called R for data science. It's not R for statistics, but there is some great information in here, practical ways to learn how to work with the R ecosystem. I have written a book where I use a lot of the tidyverse principles that are found in this book to do statistics. And so that book is also available for free online at stats4nr.com. And so you're welcome to use that book as well. And then what I'll talk about in the R code is this tidy models package. And so there's a great book, again, this one's for free, open, available on the web too, called Tidy Modeling with R, a framework for modeling in the tidyverse. And so that's there at the link there below. And so I encourage you, if you're interested in learning more about some of these concepts related to modeling within R, whether it's simple linear regression, whether it's some of these more complex, you know, more of the non-parametric things like random forests and some of the other machine learning techniques, those are available in some of these books. So I encourage you to have a look at some of those. I guess before we jump into R, I'll just stop quick and check to see if there are any questions and check into the chat. But any questions from anyone? All right, well, not hearing anything, not seeing anything, we'll jump back to it. I did want to talk a little bit more about the data. And so what we're using here is what we call the tidy models package. I mentioned that book earlier, that Tidy Modeling with R book is really the best source to learn some of these tools. But this is an R package that does modeling and statistics in addition to machine learning using the tidyverse. And so again, that's the kind of cool new way to do some data analysis in R. And so our goal is we have data on tree biomass for 7 different species. We want to fit a nonlinear model to estimate tree biomass for those different species. And so we'll kind of go through an approach, and through the code, we'll see how that relates to this tidy models package. Just a little more background on the data set that we're going to use. These are tree biomass data collected from Georgia in the United States. And so this is in the southeastern part of the state. And we'll have a look at the data here in a minute. But what they did for these trees is these are tree biomass values. So they felled the trees and then weighed them. This is not the same image from the study, but they basically weighed the trees to calculate how much biomass is in them. So this is an incredibly laborious task. If any of you have done it, maybe you know, but weighing trees that are really heavy can take a lot of time and a lot of effort. And so this is a really good data set to look at that. Again, we have data from 7 different tree species. And we are going to fit a model just like this. And so this is a model that basically uses the tree's diameter that you see along here on the x-axis and the biomass. And we're going to basically come up with a similar model for the species that we're dealing with from our study. And so it's going to be a nonlinear model that looks something like this. Any questions before we jump into R? All right, well, let's jump into R. I know we've got about 20 minutes left, so I think this set of code I'll go through a little bit more quickly, but I think we'll still be able to tell you something about just the opportunities that you could use with this Tidy Models package. So one thing I do, so I didn't close R after we did the sampling exercise. So you can either like close R Studio and then open it back up. Or one of my favorite things is I like to go up here into the little broom and just clear all the objects. And then it kind of says, do you want to clear all the objects? And I say yes. And so that will just give me a kind of like a fresh slate. So I'm not mixing my new analysis with my old analysis that you see there. And there are ways to even like clear the R console windows. So kind of starting fresh is how I like to do things. So again, like I said, with the other exercise we just did, this is the tidy regression.rmd file, the other R file that's available in that GitHub repository. And so we'll step through this as we go through the exercise. And so I'm going to read in some packages. There's a package, Tidyverse, I like that one. There's a package called Model R, Tidy Models, and then again, that G Sheet package that will help us read in Google Sheets into our R session. So I'll go ahead and click run. Sometimes on some of these packages, they provide a lot of output. It tells me here there are some conflicts with some of these different functions that are available in these different ones. And so that's not something I usually worry about, but sometimes if you're doing an analysis, you might need to say, okay, what package is it using this function from? Sometimes you might need to go back and have a look at that. So here we're going to read in the data. Again, this gsheet2 table is a function that reads in data from Google Sheets right into R. I'm going to make a species file because it turns out in my normal data file, it doesn't have the species names. And so if you look at the species names here, loblolly pine, shortleaf pine, slash pine, these are mostly pine trees that are common in the southeastern United States. And then I'm going to do some things. This is some more kind of, you might call it data wrangling, trying to get the data in the format that you want before you start working with it. I'm going to merge the tree data in that species file. I'm going to do some filtering just based on what I know about the data. I won't talk too much about that. But then I'm going to summarize the data by calculating just like the average diameter, minimum diameter, average weight of the different biomass samples and things like that. I'll click go. And then you can see my, here's my data table. I have tree species, my 7 species. I have the number of trees that I have a biomass estimate for. You can see I mostly have loblolly pine trees and shortleaf pine trees. My average diameter is here. And so these are data, again, these are data in inches. And so these are quite small trees. They're not large trees by any means. So the mean diameter is 3 inches. Say for loblolly pine, the maximum diameter is 8.5 inches. Minimum diameter is 0.7 inches. So these are mostly kind of smaller trees, just to give you some perspective there. And then we have the average weights, and then the maximum weights and minimum weights. And these are in kilograms, or sorry, pounds. These data are in pounds here. So we've got the data into R, and we've summarized them. That's good. And so our goal here is to fit a series of models that determines the above ground biomass of trees using tree diameter as a predictor. I've added also where I've obtained the data. So there's a great tool. You can have a look at this website and explore it if you want, called Legacy Tree Data, where you can filter and query this big repository of individual tree measurements that has biomass and volume estimates or volume data for different trees. And so I looked at that and I said, and I found that there are 608 total observations from these 7 different species that we might be interested in. And so you know me, I like to plot the data. So I'm just going to plot the data by diameter and above ground weight. So here's a look at the data. I'm going to make this big just so we can see it more right now. Here's a diameter in inches, the above ground dry weight in pounds. You can see quite a few small trees. it looks like, a lot of the data tend to stop here at this 5 inches. And I think that's a fact of how these trees were sampled, only for one species. And these are, I looked into this when I was looking again at this yesterday. These are the loblolly pine trees that have a lot more bigger trees, but it's only one species that has these bigger trees you see in the top right. So that's something to know as you're beginning to analyze these data. But you can see the 7 species here and kind of how they're distributed. So that's you could think that's a nonlinear line, right? It would be hard to draw a straight line through data that seemed curved like that. So this is a good example of a nonlinear regression in forestry. And so I'll step through the code some more. And so what we want to do is to fit this model of above ground tree biomass. And so again, we're going to, we see that nonlinear trend in the data. The formula that we can use is NLS for nonlinear least squares. And so that's a common one a lot of people use in R for that. And so what I'm going to do here is I'm going to say, okay, here's the model. With nonlinear models, you have to say, okay, where do you want to start the values for your parameters? Because nonlinear models are a lot more complex and a lot more difficult to fit. So you have to kind of say some values that you want here. And so as it turns out, I know another study that also fit this same model. And so that's where I got these initial starting values. And so sometimes it's hard to come up with good ones, but I was pretty confident in the ones I chose here. So I'm just going to fit a model to basically all the observations in the data, not caring about species right now. So I'm going to hit go. And you can see my output here. And so here's my estimate for my beta 0 value, and then my estimate for my beta 1 value. We haven't talked too much about p-values, but generally if you have a smaller p-value, it indicates a significant effect into your model. And so here for my beta 1 value, I see a really, really small p-value, which I like to see. And that relates to tree diameter being a good predictor of our above ground dry weight. And so here's the model fitted to all the data, irrespective of species, you can see there. But we might want to go ahead and fit. So we have these 7 different species. What we could do is we could write a lot of code that filters out the data by species, then fits the model to that species, and then do that 7 times and keep copying and pasting. But if you're a coder or you're a programmer, you might have learned that you never really want to copy and paste the same code twice because that gets to be inefficient, and you can't really reproduce that if you're doing that a lot of times. And so couldn't you use something like what's available in the Tidy Models package to come up and to fit those models for each species all in one time? And so that's what you'll be able to do. And so that's kind of what I do here beginning on line 90 is I begin to think about fitting these for all of these different species. And so I'll go ahead and run this. And you can see what I've done here is I've added the predicted line through all of those different data points. And so you see the line in red is the predicted value from our model. And I look at that and I think that's pretty good. I would be pretty happy and pretty satisfied with that. That red line goes straight through, not straight, but it goes through the data in a form you can see there. So that looks like a pretty good regression line to me. Now we can begin to look at those different tree species. And what I'm going to do here is I'm going to fit that same model, but now do it to those 7 different tree species. And so you can see that's what I do here. I call this tree coefficient, is where I'm going to store all of those different outputs from the regressions. And then I'm going to print that data set at the end. So I'll go ahead and run that. And now you can see here, wow, instead of copying and pasting 7 times and trying to keep track of it all in my R session, here I have a nice little data set that shows me for each species the term for beta 0, for beta 1. It gives me the estimates of those parameters, the standard error, the t-statistics, and then the p-values for those. And so that right there is really one of the wonderful things about the Tidy Models package, is it allows you to do all of these regressions all in one, so that you don't need to copy and paste and fit them all separately. So really, really cool way to do it that you see there. So then we can, this is a graph. Again, I use ggplot to make a graph of these different values of beta 0 and beta 1. And I try to make some labels so I can clearly kind of see what's going on. So I'll click run there. And then here, what you see here are, this is what we call a facet plot. And so we have different species going across the x-axis. And then on the y-axis, we have our two parameters, beta 0 and beta 1. And then you can see the average value for the estimate is the data point. And then the error bars represent the variability around that estimate. And so you can see these values for beta 0, they're different for every species, which you can see there. Same thing for the beta 1 values. They're different for every species. They're all kind of around 3, between 2 and 3 for most of them, but they are different. And so this is the nice thing about Tidy Models, is it gives us the way to fit all these models all at once. Well, we might begin to be interested in species-specific predictions from that model. Remember that graph a few graphs ago where I fit that red line through all the data? We might want to do that now for every species. And so that's what I do here. I calculate, I say, okay, I want to group by species here. I want to develop a species model. And then I want to basically have a look and see what that looks like by species. What you see here, what Tidy Models does, is it gives you basically a list of species. And you can see it doesn't really say what the values are here, because what it's telling you is that it's actually storing your output in a what the Tidyverse calls a tibble, which is basically a small data table. And so if you wanted to look and see, okay, for some of these different species, what's going on here, I can open up this by species object in my R window, and you can see it opens up the spreadsheet looking table here, but then there's a table nested within a table. If you really wanted to drill down and say, okay, for this species, in this case, this is sweet gum, what's going on here? And so, oh, here's the species code, here's the above ground weight, here's the biomass value. So that's cool just to see that there. And then it has a list of basically all the model attributes associated with that species. And so if you wanted to drill down, you can have a look and see what's happening there. Then we can add those predictions to the species. So now it made us a new table. So let's go again and look at the by species. And so now I can look at my data. Now I can look at my predictions if I open up for sweet gum in this case. So now it has, again, my data, and then the last column are all my predictions in pounds of what the variable or the value might be. So interesting. If we wanted to take a look, we could take a look at that some more. Let's see, scrolling down a little bit, we can make a plot of those predictions. That's what I do beginning here on line 169. So this is cool. You can see for different species, again, our loblolly pine species, we have a lot more observations. So that's why you see the line extended out farther than the other species, because we had those larger trees for the loblolly pine. But you can see that, not all of these lines are the same. And so this is taking into account our different models that we're having a look at. And then let's see some other things. Any good analysis will also look at the model residuals. And so it will kind of tell you how well your model is doing relative to the observed values. And so this last chunk of code just calculates the model residuals for your various different models that you developed. And so again, uses ggplot to create those figures. So this is one I really want to zoom in and have a look at and explain what's happening here. The way that I've written the code, so here is the residual from the model, so that observed value of biomass minus the predicted value of biomass across the range of the data here, in this case for diameter at breast height. Now the red line indicates 0, and so we would expect most of the residuals to fall plus or minus 0. And we don't really want to see a trend in the residuals. And so what the blue line shows are the trends in the residuals across the range and diameter. And so what you can see is that, yeah, it does tend to seem, if we look at Eastern white pine as an example, as the diameters get large, it seems like the model is not predicting as well or closer to 0. Same thing for shortleaf pine. Oh, but Virginia pine, it tends to predict a little bit above the value. So it's interesting to see what happens there. If we look at loblolly pine as an example, well, this is an interesting one, and I'd have to go back and take a look at the data to see what's going on here, because you can see here the residuals start to trail down about midway through the data set, but then these really big trees that we're seeing, that kind of brings it back up. And so just interesting to see that there. That's a really interesting trend. Might need to go back to see, I think it's got something to do with the fact that those trees, most of those trees weren't sampled above that. It looks like 6 inches diameter. So I might need to have a look back to see what's happening there. So that's some code to help you to get a sense of tidy models and what it can do. I really like tidy models, particularly, it seems like a lot of data sets I work with, I want to do the same thing to multiple species or multiple ownerships. And so tidy models just really helps to keep track of all that and to keep track of everything that's happening there in your R ecosystem. Yes, so I see a couple of questions. I see Jeff Peth, so I see your question. But again, if you have questions, type them into the chat. Happy to discuss more. So I'll read through yours. Determine the position to place my random variable to a random parameter under mixed effects model. For example, when should my random variable be at the intercept, slope, or both parameters? Yeah, it's a great question. There's not really a specific way to do that. And so what I suggest is try fitting your model with as many random effects on as many parameters as you can, and then compare them. And so you can compare them with a tool like the AIC. So the AIC is the Akeiki's information criterion. And so it will change as you specify these random effects differently. And so ideally, you'll select a model with the lowest value for AIC. And that can be one that you can begin to compare some of the different models that you create. So yeah, I suggest fitting lots of them and seeing kind of what happens when you look at something like AIC. And then your question on the intercept of the biomass model. Yeah, that was an interesting thing when I looked back and was running this code again. If you look back in our code, it seems to like the slope associated with the diameter term on biomass was significant and had a low p-value, but the intercept did not. The intercept, I think it was a value of about 0.3 or so, if I remember right. Yeah, and so in that case, you might, again, go ahead and take a look at the data just to make sure that you didn't do something weird like unit conversions or something like that. Might be of interest. But oftentimes, I'm less concerned if the intercept term is not significant in a model. I am concerned if the slope term is, because that's associated with the parameter that you might be interested in. But I'm not too concerned that the intercept term came out to be non-significant in that case. I think in this case, because our values for biomass and for diameter are really, really close to 0, they're really pretty small trees. I think that's why we're seeing that that intercept term come out to be not significant, because that line is really, really close to the 0, mark on both axes. So that's my initial thought there, Japeth, about what's going on there. No other questions or?
Yeah, we have a question that I'm going to read out. and it's about the model diagnostics. So the question is, how much of diagnostics should we carry out to ascertain the efficacy of the model? You speak about AIC, the archaic information criterion, to judge the efficacy of this model. And can one also make use of the BIC? I think there is something called the Bayesian information criterion. And so this is the question the fellow is asking.
Yeah, it's a good question. I do encourage you to have a look after you develop your model, to have a look at the residuals. And that goes back to my point of, even before you do statistics or you do modeling, visualize the data, then do the modeling, then be sure to visualize the results. It's really important to look at the diagnostics like that. And there are certain things like you can look at with linear regression model that you don't necessarily need to look at for a nonlinear regression model. But you do have other options depending on what kind of modeling framework you do. And so, yeah, the AIC term, I really like that because it allows you to compare different models. And so, the previous question about, how to specify my random effects is an important one. So you can begin to use AIC, or the BIC, the Bayesian information criterion, is very, very similar to the AIC in a lot of ways. And so I encourage you to have a look at those to really find the best model. And what I like about the AIC or the BIC is it penalizes you for having too complex a model. And so in that ways, it really, the number of parameters in the model is a parameter in the calculation of AIC. And so what AIC really wants is a really, really good model, what we call a parsimonious model that fits well with as few variables as possible. And I think that's a really good one, especially for us in forestry. We like to have really good models that can be applied broadly. And so really think about how some of these diagnostic tools can help you when you go to not just looking at how you can use modeling to inform what it says about your data, but applying it outside of your data set as well.
Okay, so I think there is a question, like an additional question to what he asked. So should I adopt the model or discard it since its intercept is not significant?
Yeah, I would still go ahead and use the model that has that intercept that's not significant, just because you maintain the structure of the model form and all of that. Now you could remove that and try fitting a no intercept model. Sometimes those don't work all that well with nonlinear models. Sometimes they work pretty good if you're just looking at a linear model. So yeah, I think in this case, because it's on the intercept term, okay to use it if it's still not significant in its application.
Okay, there is a question I'm going to read again. So this fellow is trying to ask that you spoke about transforming a data to conform to the normal distribution. And so he's asking, like the example you cited, using the biomass against the pH of the tree. So he's saying in such a scenario, would it also make some sense if it tries to transform the data and then fit a linear regression?
Yeah, that would be another thing, is to, so we use the nonlinear form, but you could also do like a logarithmic transformation of the X variable and possibly the Y variable of the diameter, breast height, and of the weight of the tree. And that could also get you a pretty good estimate, and you could just use linear regression. For that case, I would think about and encourage you to plot the data before you ran some of those statistical models, to see if those data are normally distributed after you transform them. That's generally, that logarithmic transformation is going to do a lot. And it's really handy for foresters to use with any kind of biological data, just because it tends to make things more normally distributed, that we could use more statistical methods to run in our favor.
Okay, I will just take this last question and then we close for today, because we have some more people trying to ask some questions. But this is a question on clarification about the fixed sample plots that you talked about and variable plots. So he's trying to ask that, can you please, in just a minute, go over it again for him to be clarified?
Yeah. So with the fixed area plots, you're generally, putting forth, into the woods, into the forest, you're measuring a fixed area of land. And so that could be, 1/10 of a hectare that you're going to measure. We generally never measure at large plots like 1 hectare in size, unless you're in like a really specific research station or doing something for an experiment. And so with the fixed area plot, you're going to sample trees that are within that 1/10 of a hectare. And so the idea there being that you can measure maybe a few of those, in a stand of trees to give you a sense of the variability that's happening in that stand. Now with the point sampling approach, in that approach, we're basically assuming that every tree has its own plot surrounding it, and your center of your plot is going to count all the trees whose plots around it are counted within where you're standing. And so it's a really unique way of sampling, and it really encourages you to sample trees relative to their size rather than how frequent they are across the forest of interest. And so in many ways, in a lot of companies, a lot of industry people, they really like to use the point sampling because it's more efficient in the field. You can do point sampling with like one person crew going out into the woods, whereas fixed area sampling, sometimes it's better to have 2 people because you need another person to manage the other side of the tape to tell you how far away you are from plot center. Whereas, like I said, with point sampling, you never really have to measure the diameters of trees because standing in one area with your prism or any angle gauge that you're using, you can tally the trees by standing in place. And so the point sampling generally more efficient than the fixed area sampling, but both have advantages and disadvantages.
Well, thank you very much for that wonderful clarification and for the awesome lecture you delivered today to us. We are very grateful, and on behalf of the organization and the participants, we want to say a big thank you to you, Dr. Matruzel. And I'm sure in the next time, because we still have more of this series, like I told you, we hope to bring more people. Like I was talking, was it with Professor Aaron Aaron from Maine? I know he's also from the University of Maine. So we are really grateful for the time you have created out of your very busy schedule to be with us today. Thank you very, very much. So for those who are requesting for the video, this whole thing is shared live on our Facebook page, and as well, it will be shared on our YouTube channel. But so if you're not following us on Facebook, you can easily search for tag NG, and then you can have access to the video. You can watch at your convenient time because a lot has been said by Dr. today about how we can do some basic sampling designs and statistical approach in forestry. So like he said, it's not going to be something easy for you to follow through line after line, but you have the materials shared on the GitHub link that was dropped on the chat. And myself too, on my computer right now, I have on my R platform, I have the whole codes. I have tested everything that Dr. did today. And after this whole tutorial again, I'm going over it again to apply all this to something new. And there is something I saw again, and for me, it's new, Doctor. There is a book you shared that you wrote that statistics in natural resources. This is also what I would recommend that everyone should get. And thank you for sharing this book with us and the link for us to have access to the book. Myself, oh, interesting. So I'm going to ensure that we share this with everyone on the platform, on the WhatsApp platform where we have for participants, so they can all read. And if they have any kind of questions they want to ask, they can send to us and we'll reach out to you. So once again, we want to say a big thank you to you, Dr. Matruzel, for your time and for the kind of passion you have to impact the lives of young African people. On behalf of the whole organization, we want to say a big thank you. And we have one of us that is here with us, Mr. Blessing. Thank you for joining us. And the rest participants, we also want to say a big thank you. So, Professor, we would, in the next edition, I hope if we reach out to you, you would also give us this awesome welcome again. Yeah. Okay. Ciao. Thank you, everyone.
Great. Thank you, everyone. I enjoyed our time today, and best wishes to all of you.